This program on your cell phone, okay? Yes, it's a Kahoot. Or if you don't want, so you can use the web browser. Later I will explain. The Kahoot.it. It's a what does it stand for? Italy or IT? Which country is that? Oh yeah, app. You can install the Kahoot, or if you don't want to install, so you can open the browser with the Kahoot.it. Which country is that? .it. Is it country name or the country domain, or just the IT? I don't know. But anyway, I will explain later. Okay, so we are going to continue the memory, the management, especially for the paging. So we are talking about the page replacement algorithm because we do not have the enough page frame, so we need to replace. So we cannot use the swap in and out because it costs a lot of the transfer. So in terms of performance, it's not so good. So we consider the fixed size of the data structure, both the physical memory as well as the logical memory. Logical memory means it's a program. Then page by page, we can page in and out. Sometimes we do not have the free page frame in your memory. At that time, we can consider the page replacement algorithm. So first algorithm that we have considered is the first in, first out, which means don't forget the first, this one, the first first three. This one is a page fault because we do not have, we cannot find the page, desired page on the page frame. The first three, the paging is caused the page fault then. So 4, 1, 2, 5 is not a problem. 4. There's no 4, so we need to take a look at which one is the first one. So 1 is the oldest one, so we can replace by the new one. So that causes the page fault, so page replacement, and so on. So for example, the 5, so if we, the page in the 5 page string, there is no available page frame, so we need to find the victim page. So to decide the victim page, which one is first in. So among the 4, 1 to 4 was in the this time, 1 was in this time, and 2 was in the this time. So 4 is the oldest one, so we can replace the this one by the new one. So that is the first in, first out. So we have seen the delayed anomaly, even though we have the 4 the page frames, and this one is a 3-page frame. The 4th-page frame caused more the page fault, that is anomaly situation. It's called the delayed anomaly. The reason is that depending on the pattern of the page string. So we will think about such a thing later at the end of today's class. So probably you practice at your home. We are using the 2 different page reference string, so you probably practice by yourself. Okay. The next one is optimal algorithm. Instead of seeing the past, why don't we take a look at the future? If the page will be used soon, we try to keep it. Otherwise, we will replace. That is the optimal algorithm. For example, the first 4 frame causes the page fault, and the 1 is reused. So there is no problem to reuse this one. It's no problem. But in case of 5, there is no 5 pages. We need to select one of the pages as a victim. At that time, we take a look at the future. 1 will be used this time, and 2 will be used this time. 3 will be used this time. 4 will be used this time. So 4 will be used later. So we can replace it. Yes.
How many future frames we have to check, pages we have to check? All of them?
It depends. It depends. At this time, we take a look at up to this one because that's the end of the page string. Okay, there is no further the program are running. But anyway, the optimal algorithm is good. It's the best one in terms of algorithm, but it's not practical. Yes. So it can be used for the reference algorithm. For example, I have the new algorithm for the page replacement. Then you can compare the performance with this one. What is the average page fault for the given the page string, something like that. Okay. And this is the optimal algorithm. So why don't you practice the another one? Then we briefly take a look at about the least recently used algorithm. Anyway, the optimal algorithm is not practical because you need to see there is an algorithm, there is the approach to see you cannot see the future, but you can guess or estimate the future. So we will see briefly about that later. But for practical reason, why don't we take a look back? Okay. However, instead of the arrival time, if the page has been used a lot, then we can keep it. Otherwise, we can select that page as a victim. That is called the least recently used algorithm. In case of the 5, okay, this time, 1 was referenced this time. Okay, 1, and 2 was referenced this time, and 3 was referenced this time, and 4 was the reference this time. So 3, this page was the least recently used one. Okay, then it may be less chance to be reused. So we will select this one as a victim page and so on. So total number of page fault is 8 pages. So it's better than the first in first one. Not better than the optimal, but it's better than the first in first one. Problem?
Track of the
yes, we need to keep track of for each what about the first in first one? First in first out, the arrival time or replace time will not be changed. However, for each page frame, the last reference time will be changed and how many times is referenced. So that data, that count should be changed. So we need to keep track of such a history of the referencing for each page. So that is cost a lot of computation and a lot of space, waste of the space. So there are two basic approaches to implement the least recently used algorithm. First approach is, as you can imagine, count. Okay, we can count how many times is used. So for each, not the first how long. Since is last reference, how long? At that time, instead of measuring the time, so we can count. So we get for example, this, as I said the last time, I'm trying to get used to use this one because I usually keep it, but it's not. This is a time, okay? So this is the time. Sometimes when I touch, it's moved to the next slide. But without touching, I cannot write. So this is a time. Then every time slot, it can be millisecond, it can be the microsecond. It depends on the characteristic of your system. The given time, every time we can increase the number of count that is assigned for each page frame. So for example, this time is 1, and the next time. So let's say this is a T0, 1, 2, 3, 4, 5, and so on. Then when T is equal to 1, it's increased by 1, so the counter is 2. And 2 is first, so it's in the second page frame is 1, and so on. And at time 2, the 3 is loaded into the page frame is 1, the other increased by 2. Okay, what happened? The 1 is referenced. Okay, 1 in case reference is a reset because it's recently used. So we reset the count to 1. The other increased by 1. So when the page is referenced, it's a reset to 1, 1, 0, whatever. Then the other page frames count increased by 1. Then when we select the page, the victim page, wow, we have many students in the morning. I'd like to compensate today also. So 5, we cannot find the 5 here, which can be the victim pages. We can take a look at this, right? The count, the lowest one or highest one. Highest one is not the used recently, right? So lowest one is recently used. The highest one, for example, this one is the loading, the reference used this time. So we can just select the highest count, the page frame as a victim. Okay. So to do that, when you implement the LRU algorithm with the counter implementation, we should create the counter data structure for each frame. And also, what is the size? There might be a limitation you need to decide, like the integer, so 4 byte for each page frame, it will be huge. Also, you need to, the plus and you need to select the highest number to decide the victim. So it's the time consuming a lot, but you can implement using the LRU algorithm using counter. Any other way to simplify such an implementation of the LRU? Because in your project B, you need to select one of the approach. Okay, if we have a better idea, we can do that, but most of the students will use either of the counter or the second one is using step data structure. What is a step? First in, first out? Last in, first out. Okay? It's a kind of step up. You can step up your book, then you cannot pull out the bottom one. Just the top one you can pull out. But in our step structure, it's a slightly different step structure. So let's say this is the step. This is the enter. So you have the number of, I can keep the number of the item here. Okay? Then in the step, we can take out the bottom one, okay? Instead of the top, pop out the top one, okay? We can take out the bottom one. Then the other will move to such a way. Okay? So that is it's not a big deal to implement because we are not going to move the item by item when we implement. It's just a referencing. Okay, so doubly linked or singly linked. In this case, we can use this doubly linked, the stack structure.
Basically, it's a queue, right? Instead of stack, queue is
But the queue is you can just in and out, but who is why we consider such a slightly different the stack data structure. Okay, so for example, this one. Let's see this is the how many page frame? 4 page frame. So in this case, the 4 page frame, and how many the logical pages here? So in this case, 1, 2, 3, 4, 1, 2. It's 5. Okay. So we are going to create the 6. The data item, the stack structure is a bottom, and this is a top. Okay. Then, if the page is reference and the put, okay, put into the step. So this is bottom, and 2, 3, 4 up to this one. So which one will be this one? Which one will be least recently used one? 4 is least recently used one, and the bottom one is least recently used one. So we can pull out the bottom one as a victim. Always. We don't have to calculate. Okay? We don't have to increase the counter. Okay? Instead, we can just pull out. Don't be, it's not always. This is the time. Okay? Time by time. So we have only one step data structure. This is the time step at time 2, time 3, time 4. Okay? Some of the students try to create the array, the 2-dimensional array. No. This is the one-step structure, and so on. Then, what if the page is referenced? So this time 1 is referenced at the time. We can move the reference string to the top. Okay? How can you do that? Do you need to copy the data item? No. We can just change the reference in your step. Okay? this is the single or doubly linked list. In this case, I think the doubly linked list. So we can change the pointer of this one to in this case, the bottom, and then 3, 4, and 1 reference the 4 like that. Then 1 is the recently used one. Then this time the 2 is the least recently used one. So in case of reference, we can move the top. Okay, so we can see the top is the recently used one, and bottom is always the least recently used one. What if the 5? So we cannot find the 5, so we can just select the bottom one, the 3 as the victim. Okay, then put the 5 on the top, and this will be removed. Okay, then we can keep the stack structure and so on. Is it better than the counter? Yes, we can use only the 6, the data item, and also we don't have to calculate, but still we need the space, memory space, considering the number of page frame. Right? So when we have the 1,000 page frame, then we need to manage the 1,000 data item, the stack data structure on the memory. Okay, but it's better than the counter. So in your project 2, you can select either the stack approach or counter approach to implement the LRU algorithm. Okay. Also, it's welcome anyone who is thinking about the new algorithm, then compare which one is better. When I was a student for the faculty research days, the poster or the project or SE, so many of the students actually slightly changed the algorithm and compare with the existing one like the optimal or the step-based algorithm, and 10% increase the performance. So at the 10% decrease in page 4, then that can be published as a classroom project to be published. But nowadays, I cannot see such a thing. Okay, so we can use the counter implementation and stack implementation, but still they need they do not cause any delays normally, but that depends on the number of page frames. So still not very efficient algorithm. Is there any other way? So yes. So there is another way of implementing algorithm. That is the LRU approximation algorithm. Instead of the managing all the history of the reference, the page frame, we are going to simplify such a reference, the history. So using the reference bit. So in this case, one of the approaches. Let's say we have the 4 page frames. Page frame number 0, 1, 2, 3. So once each page frame has a number of the bit. So let's say the 1 byte. 1 byte for each. So how many bit? 8 bit. So then this one has the 8 bit also, and this one has the 8 bit, and this one has the 8 bit. If reference, okay, if reference, that is set as the 1 from most significant bit. What is the MSB? It's left or right? Left, because the number starts from the right. So least significant bit and the most significant bit. It's the MSB and LSB. From the MSB, so if reference, for example, this one is a reference, then the 1. Otherwise, 0. Okay? It's not used. Then the next time slot, so if reference, this one is the reference, then shift right. All the bit shift right. So this one is a shift right. This one 0, 0, and 0. Then the not reference 0, reference 1, not reference 0, not reference 0, and so on. next time slot, if this one is a reference, shift right. Okay, this one is 1. Shift right. So 0, 1, 1, 0, 0, 0, and 0, 0. And this is a not reference 0. Not reference 0, and reference 1, and not reference 0, and so on. Shift right, shift right, shift right, every time slot. Okay. Then, first question, how long? How many time slots can we keep track of using this reference bit? In this case, how many time slots? 8. Okay, so this is not the entire the history of the page reference. It's sometimes the cost a lot of space. So that is the reason it's called the approximation. Okay, we are not going to keep track of the entire page, instead given time. So in this case, 8 bit. Okay, then that is the first question. Then when we select the bit, which one will be selected? How can we select the bit?
The one with the most significant one.
In other words,
the least recently used.
highest number. Okay, biggest number.
Yeah.
So biggest number from the most significant bit, check the biggest number because that is the MSB. Okay, if we have the time, then next bit, next bit. Then we can select the highest number as a bit 1 because highest number, lowest number, lowest half digit because its reference is 1, right? Not reference, it's a 0. So if never referenced, never used, it's a 0, which means it's least recently used. So we will select, don't be confused. So lowest number will be selected. From the most significant bit, you can select the 0. Okay? What is the difference between counter and this one?
It's using less memory.
Less memory. And second? Less iteration. Fast. Efficient. 1. We use only
8 bits.
the shift operation. Who provide the shift operation? Processor. Okay, the instruction level, hardware level, it's a very fast, not software implementation. Okay, even select the lowest number, it's not a big deal. We can just compare the most significant bit and right, the next. So it's a very fast because it's a hardware implemented. We can get the benefit. The difference is it can keep the only limited time slot. So that is the reason it's called the LRU algorithm. So you need to select the proper size of this one considering the characteristic of your operating system.
Professor,
Yes.
but we don't need to keep the history of all the pages.
No.
The
So
only-
that's the idea,
Yep.
right?
The only pages that we are worried about is the current page frames that we can access in a particular
Yeah, it
time.
depends on the page frame, not the pages. It's the physical. However, we need to keep track of all the page frames, but not keep track of entire history, limited history. Okay, that is using the reference bit. Still, you need the 8-bit or sometimes the 16-bit, depending on the size of the history per page frame. So another approach for the error approximation is a second chance page replacement algorithm. Idea is, so we are going to assign the 1 bit. I think that this one is better than the pen. 1 bit. Okay, even 1 bit per the page frame. Then we will consider this one as the first in, first out. But the last, the input is linked to the output, which means it's a circular, the first in, first out. Okay, it's a circular fashion. So circular, so same as the first in. So start from here, but that is linked from the end of the FIFO. Then same idea, if not reference 0, if reference 1, if not reference 0, not the first one. Okay? So our goal is to find the first one. 0. Okay? The 0 is not reference. For example, if we start from here, this one will be the victim. It's not the best optimal, but our goal is to reduce the overhead. Instead, we try to increase the performance, less space, and faster, efficient algorithm. Even though it's not the optimal the selection, but we try to find the victim page. Okay? So what if? Or then, this one, we start from here. Okay? Start from here. Then next, this one is selected as a victim. Okay? Then it will be changed 1. Then next turn, the starting point is moved to the here. Then our goal is to find first the 0 bit. So this one is 1. So we skip, move to the next. Then at the time, change. Whenever you check, we change this one as a 0. We will see 1. Then move to this one is a 0. So it will be selected as the victim. Then change it 1. Okay? Then the next time when we find the victim, so this one, we will not start from the beginning because it's not fair. So next one, this one is the 1. So move to there. This one, beginning, and the service is a circular FIFO. Then this one, so move to this one will be selected as the victim. Okay? And so on. However, if all of them are 0, like this one, okay, all of them are 0, then move next, forever. So that is the reason whenever we move to the next one, we will change reference bit as 1. So next time, it will be selected. So that is the reason it's called the second chance. At most, it's just one cycle of the checking the bit. Okay? So, benefit is only the 1 bit per the page frame. Okay? And the complexity is just the number of the page frame. It's one round. It's a linear. That's it. So that is the second chance, the page replacement algorithm. Obviously, it's not the optimal solution. It's the approximation. Okay. There's another one. It's a little bit enhanced second chance algorithm. So we consider only the reference, whether referenced or not. Okay. However, what if the page is changing? That is called dirty. So I said this is a change into the file. So this is called dirty buffer, dirty page. Okay, there's a dirty bit. It's a 1 or 0, whether it's a changed or not. That changed buffer may be reused soon. So that's the idea. So not only just reference one, whether modified one. So plus one more bit, it's a reference bit and modified bit. So in case 0000 means it's not referenced and also not modified, this is a higher chance to be selected as the victim. Because it's not selected, not the modified. And other case is that it's not referenced but it's modified. And it's a reference but not modified. Reference and modified. These are the higher chance to be reused. So we try to keep this one, and but we can select as a victim for the not changed and not referenced. This is the enhanced second chance the algorithm by considering the modified bit. Okay. So we have learned about the FIFO and optimal and the error value. For the error value algorithm, we use the counter and also step and also the estimate, the approximation algorithm, and also second chance, enhance the second chance. In your the project 0, this is not a programming contest, okay? It's not programming language class, so I don't consider any the fancy, nice graphical user interface. Instead, whether you are going to implement correctly for the requirement. So please read carefully the project. It's exactly the same thing. Project requirement, so that the output should be correct. Okay. That as indicated in the project description. So you are going to implement the 3 algorithms, first in, first out, optimal, and this one, the LLU algorithm. For the LLU algorithm, it's up to you the approach you are going to use, either the step or the counter. But you need to specify in your writing up or the readme file. I select this one for the implementation. Okay. There is another approach. What if we consider frequently used one? It's the opposite of the least recently used one instead of the frequency of that. Okay. Obviously, it's nice to select the least frequently used one. However, sometimes you can select the victim most frequently used one. For what? In case page, if you know the pages are uniformly accessed, okay? It's your knowledge, it's your experience. So most of the pages are uniformly accessed, but some of them are frequently used, which means the least frequently used one may be accessed again, because it's on average it's the least uniformly accessed. So you can sometimes, depending on the situation, you can select the frequency to select the victim. Okay. That's all for the page replacement algorithm. There are several other issues that we are going to discuss because we have many attendants today. I'd like to have something very interesting quiz. Is there anyone who do not have cell phone? At least you have a cell phone. You do not have. So why don't you work with your friend? So either if you have the laptop or the browser, why don't you log in Kahoot.it? Why don't you log on to this one? We will see if I consider this one as a part of the grading, I will ask your UB ID, those who put the name or the other ID. Okay. I do not know whether I can use the result correctly because it's my first time. Okay. Most of the rest of the part of the chapter 9, so we will see how to enhance the performance for the paging and the page replacement algorithm. One thing is instead of select the victim whenever we need, why don't we try to keep the pool of the free page frame? Then if needed, then assign. Which means even though page is not free page frames are not needed during the idle time, during the computer research are used. Then at that time, we'd like to select the victim for future. Okay, then keep that as the pool of the free frame. Then assign. Whenever we need it, we can assign the page frame. That is called the page buffering, the algorithm. Okay. Also, some of the application need to access the data in the hard disk drive or the file system. In that think about the database system. Database management system is the application level. It's not operating system like the other PowerPoint or Excel file was. So it's the application level running on top of the operating system. They need such a page replacement algorithm or so on. However, they need to access the data on the file system a lot. So for the specific application of the page replacement, we will consider the instead of the assigning the free pages, we are going to use the low disk. The low disk means we can, without using the file system, we can directly use for example, when you attach your new hard disk drive, it will be recognized as the DEV device. In terms of the operating system perspective, any resource will be, it's a file, okay? Device is a file, so it has a file pointer like the HDA0 and so on. So also, if we know the algorithm used in the disk controller device program, we can directly access the data in the hard disk drive, low device. At that time, we can get the better performance rather than using file system. File system, there are a lot of algorithms, read, write, so manage the file and manage the directory. Instead, we can directly access the data. Okay. Then operating system utilizes such a low device to access the data in the hard disk drive instead of the allocate the pages for the specific purpose, like the DBMS the system. Somebody said because of that, the DBMS database management system is kind of in between operating system and application program. The DBMS itself, they are actually the controlling or the managing the resource directly. Okay, one time the Oracle, actually everybody knows what is the Oracle company right now. The Oracle, developed the database operating system. They integrate the DBMS and the operating system. Do you think was it successful? No, because you cannot see such an operating system, such as the DBMS. Because the DBMS itself has their own functionality. Even though they integrate the operating system part, they cannot get the better. Also, many of the customers are familiar with to use the operating system and to see the application part from the operating system perspective. Okay, at the time, so this is for specific application we can increase the performance. Another issues in the page management is how to allocate the frame to the process. Okay, so far we have discussed about how to decide the victim and how to replace the page in and out. However, when we start a new process, we need to allocate. So in terms of on-demand pages, if we consider the extreme case, only one page is needed, right? First page, then next. That's the on-demand. However, you can imagine that the approach will be slower. Instead, if needed, so why don't we replace a group of pages together? For example, the IBM 370, they need 6 pages for the move instruction. Okay, so which means not just one page by page victim page. We need a group of the frame, minimum number of pages. Okay, so there are two approaches. One is the fixed allocation. Another one is the priority allocation. Fixed allocation means the operating system assign a number of pages for the new process, like the 6 pages first, okay, and the 10 pages first. So that is the fixed allocation. However, so depending on the priority of the process, some of the process need more. So by considering the priority, so at that time priority can be explicitly assigned the priority, but mostly it's the size of the process, size of the program. Considering size of the program, so we can provide a number of the pages that is the priority-based allocation. So how can we calculate? It's just a simple math, okay? So by considering the priority, in this time priority is the size, we can provide a number of pages at the free page frame to be allocated. That is the priority allocation. Global and the local allocation means, so when we select the victim, so far we can select the victim page from the entire page frame. That is called the global allocation. However, if we consider the victim page only the pages that are allocated to the specific process, is called the local allocation. Even though there are free frames, if the process is not using that frame, you cannot get the free frame. Okay? Instead, among the pages that are allocated to the process, you can find the victim page. This is the local replacement. This one provides more consistent process performance. We can guarantee the performance. That doesn't mean it's better. It's we can guarantee consistent the performance, but it may be underutilization because we can, even though there exists the free frames, we cannot get the free frame. What about the NUMA architecture? What is a NUMA? Not Puma. What is the opposite of the NUMA architecture? SMP, symmetry massive process. Logically, even though you have a number of CPU, logically it's considered as 1. Okay, you need only one scheduler, and it's your program is now you don't have to worry about the parallel processing. The operating system will take care of everything. So the SMP NUMA architecture is each one has their not dedicated, it's the affiliated, but you can still access this is a memory level, this is a CPU level. You can still have a chance. However, this one has the most priority. Your update data will be here. Then this one will be accessed by other CPU, but it's slower. Okay? So non-uniform. In the SMP, you have the CPU and you have the memory. It's a uniformly. It's the same chance. It's change it, then other process can access. But this time, so it's there exists the affiliated, the memory, but you still have. If you do not consider this one, disconnect, it's called the MPP. It's a shared nothing distributed the system. Okay? So shared nothing distributed system is totally different story. But the NUMA architecture allows to access the data, modified data in the other affiliated memory, but it's slower. That is called the non-uniform memory access, the NUMA architecture. It's the same thing. In the page replacement, you can find the victim from the affiliated one. That is the idea of the page replacement in the NUMA architecture. That is called the I group, which I do not know much about. Okay, but if you understand what is a NUMA, so you can understand how it works on the NUMA architecture for the page replacement. Next topic is the thrashing. Do you remember the belated algorithm? Belated algorithm due to the pattern of accessing the data pages. Even though we have the more the page frame, we have the more page fault. Okay, that may happen. Similar the situation will be happen in real life system. Let's take a look at this one. So we have the big, not just the 4 frames or 5 frames. We have the fixed size of the physical memory, and which allows the multi-program. So this is the degree of multi-program, which means you execute more and more processes. More and more process, then CPU utilization is going up. At certain point, CPU utilization will be dropped. Why? We have too many processes. This is a physical memory, and we have the too many logical memory. In other words, too many number of processes. Even the virtual memory is full. solution, replacement. So certain time you have a lot of replacement. So that time is called the thrashing. However, thrashing does not mean always we have the lack of the memory. Okay, why? Because let's take a look at this simple example. It's a pseudocode of the adder 1 through 100,000. Okay, so we write adder, then save into the A. Okay, I think there should be AI. Am I correct?
Yeah.
But anyway, so it's not important. Just take a look at. So we have the 4 frames. Okay, 4 page. This is a memory. Page frame. So 0, 1, 2, 3. First, this right now A is in the first page frame. Main function is 1, and X is here, and B is here. Okay. Then we need to wrote this one I. Okay. We need to select one of them as a victim. So this is I. So page fault. Then if you learn that this one, we need A. So A, so we can select this one as the victim. So A. So page fault plus. And then next, so we need, next time we need A again, so we select the X. So every routine we have page fault. Okay? So that causes, this is a very simple example that will happen when we have such a the multi-degree programming, multiple process are running. At certain time, we have a lot of page fault. So that situation is called threading. Not threading, so thrashing. How can we solve that problem? Anyway, we cannot increase the physical memory. If we can add, yes, this is, but it's limited. To reduce the page fault, why don't we group the pages? They are working together. Okay? Then anyway, we can minimize. We can reduce such a page fault. So that is called working set model. So we are going to consider locality. Locality of the pages. If think about the, for example, the one routine, main function, let's say have the 2 or 3 pages. 3 pages, the instruction that run the main function, these 3 will work together. We are not going to select one of them as the victim pages. Okay? Instead, we consider the group of set of the pages as a working set model. Problem, how can we design such a working set model? From the source code, from the process, it's not easy to identify which one will be. We need to, the operating system should know all the logical, the algorithm, flow, everything. So instead, so this is one of the approaches to find the locality. This is a time. Okay, at certain time, this is a certain time. So this is a page number. If they are in the memory, it's here. Okay. So you can see some of them are grouped like this. This time, during this time, it's a group. Okay. So by using, this is one of the approaches to find the locality, not analyzing all the process, not analyzing all the program. Even one program, it can be this way, so it's not easy. Instead, we are going to visualize. This is one of the visualization of such a memory reference pattern. So using such a thing, we can make the group. That is a working set model. So for example, you can see page number 1, 2, 5, 6, 7. 1, 2, 5, 6, 7 are working together here. In this case, the 3 and 4 are working together here. So we are going to say this is the group of the working set. Group of the page, they are working together. We can, if the memory size is less than this working set, then may cause the trashing. Okay? Because we need 1, 2, 3, 4, 5 pages, but if we have 4, definitely during that time, we will cause the trashing. So we need to keep track of such the working set model to minimize the page fault. Okay. Another approach is using the page fault frequency. So we'd like to keep, so this is actually it's the number of frames, and y-axis shows the page fault rate. So we'd like to keep the middle. So this one means we have a lot of trashing. We need more space. This one is less utilization. Okay, less utilization. We'd like to keep such in the middle by considering different size of the locality working set model. Okay. There is another approach for better performance of the page replacement is a MemoryMap file. Actually, this one is used for the real I/O, the better performance of the file I/O. The MemoryMap file means, so we have the disk file. It doesn't have to be the program. It can be data file. So even the data file I/O, some of the operating system use this one. The Windows API and the Linux API, they use this approach. This one is directly mapped to the physical memory frame. Okay, instead of the memory structure, without using the virtual memory, the concept. So they are mapped directly. Okay? Then, what is the benefit of using this directly map the disk file to the memory map? There will be less overhead of using the system code. Okay? Write and read the system code without such a system code. We can directly access the data. Such an approach can be used for page replacement. So for the program-wide, we can map the disk file to the memory without using the virtual memory. Instead, the process, especially for example, shared library. In case of shared library, they are not part of the process, but they need to access such a shared file. Shared file without using the virtual memory area, so directly map to the page frame from the disk file. Then if they know the page frame number, they should be able to access such a shared file. That is called memory mapped file that are different from the traditional, the system code, which is called MemoryMap. I never used, but you can find some of the source code from the textbook. Yes.
The file is basically residing into the memory when we call the mmap or create file mapping in Windows.
Mm-hmm.
What if the memory is already filled and we cannot have another file mapping? So what could happen actually?
What happened when the file is already...
We already have a file mapping and there is another process that's trying to make another file mapping.
For the same file or the different file?
Any other file, yeah.
So for the different file, they can map their own mapping. So for example here.
The question is actually if the...
Yeah, so if you have another file, okay? So they can use this one.
There is no space in memory.
Yes, in that case, so there's no space, then you can select I'm not sure whether this can be the victim pages. Okay, I need to check, but they definitely find the victim pages for the replacement to get the free frames. Okay. So to implement this, so you can use this. I think one or two students I heard from the ISG, so use this one, system core, and not this class, the last semester, to implement the file system. So MemoryMap, okay, which I never use, but I don't think you need to use this one, but the database class may be needed to use this system core, okay. When will be returned? Instead of the page replacements, I think it's during the close time, so the map file from the memory will be returned, okay, as a free. Okay. Allocating. So far we do not differentiate the user, the program, and the kernel program. 2 more minutes. So allocating the kernel into the memory is slightly different. They need the contiguous, sometimes the contiguous, the memory space. So because of that, the beginning part of the memory, physical memory, is allocated to the operating system. Okay, then they will be used. That part can be managed. Several other algorithms, like for example the body system allocator. So this is the beginning part, 256 is allocated to the kernel operating system. Then if we need a smaller size, because it's a contiguous part without considering pages, so it can be divided into two. So because of that, it's called the power of two allocator. Left hand lower and left to right. So until they need the proper size of the memory, then allocate. This can be easily combined. It's called the coalesce. So they can be combined, so they can keep the contiguous size of the memory for the kernel allocator. I'm going to skip the slot part. Slot is another data structure to allocate the kernel between the kernel object and the group of slot is not the fixed size, the memory data structure, unlike the pages, is the contiguous kind of pages. It's called the slot. Okay. The last part of the chapter 9. So there are several things we need to consider for the page replacement. Pre-paging. Before the user start the program or the execute the program, some of the pages is already allocated to the memory. For what? Better response time. So for example, startup file. So during the starting of your operating system, some of the application which will be used, definitely used, or selected, will be loaded into the memory, allocated. Then when user start the program, doesn't have to be loaded into the page in, it's already in the memory. Then it will should give the faster response time. So pre-paging. Okay? And also page size. So page size, the smaller is the better in terms of internal fragmentation. However, they still need I/O, page in and out I/O. So the bigger is the better, then it will be the waste of the internal, the page space. So because of that, for example, some operating system provide dynamically changing the page size. Okay, so from the 512 byte, it can be increased up to several megabytes. Okay, so that is the issue by considering performance. Even the programming level, you can reduce the page fault. Probably you learn which one is better. Obviously, you learn that this way. I, J, the outer loop is the first dimension of the array. The inner loop is the second dimension. Why? Why this one is better than this one? In your programming, the undergraduate level or beginner, the programming level course, you learn the output is not different. Okay, performance will be different. Why? Basically, this is a reference, right?
continuously accessing
Yes.
memories.
So this is your process. So in your heap area is a point. This one, this one, this one, and next. However, if you access the opposite way, J is here, but every time you need to access the data, then that will cause the page in and out. So it's not continuous pages. So because of that, in your programming, so you can, not only this one, there are several other things. So you can find the very nice article how to optimize your program by considering such a thing. Okay? These are the example of the page replacement. The Linux and Windows, you can quickly take a look at. Okay, that's it. Any questions? We will continue the I/O management from the next class.